All right. Hello and welcome everyone. Thanks for joining on this webinar with Sofar and Aanderaa focused on subsurface current measurements. Super excited to be talking with you all today. My name is Dan Breyre. I'm Sofar Ocean's product lead focused on Spotter, and I'm really excited to be joined by Aanderaa's product manager and scientific advisor, Anders Tengberg. Hey, Anders, how's it going?
Hello. Hi.
Before diving into this really exciting webinar, a couple key things that we want to touch on just from a housekeeping standpoint. First of all, this session is being recorded and will be shared afterwards. Also, if you have any questions, feel free to add them to the Q&A box right at the bottom of the actual screen. We'll be monitoring it throughout the webinar, and at the end, we'll have time for any questions that we'll be able to field. So with that, let's jump in. Uh, for those of you not familiar with Sofar Ocean, we're actually an ocean tech startup based in San Francisco. Our goal is to close the ocean data gap, and that came about because our CEO, who is a PhD in ocean science, founded it with the principle that there's just not enough observational data to do the impactful work that is needed for our planet, which is primarily ocean-based. And that's the kind of principle around Sofar. The reason why this exists is because collecting ocean data is really hard. Uh, Ostensibly, we don't put any technology in a more difficult environment than the oceans. And as a result, the technology that exists now is large, complex, expensive, oftentimes requires engineers to integrate or to operate. And that all equates to just bespoke systems that are kind of unwieldy and difficult to collect the spatial coverage that was really required. To solve this problem, Sofar really focused on our platform of a surface buoy called the Spotter. And this is a small mid-ocean buoy about the size of a basketball, small enough for us to be able to deploy it from a kayak or stand-up paddleboard, but tough enough for us to throw it out of helicopters and aircraft. And with this small platform, we're able to capture waves, wind, sea surface temperature, atmospheric pressure, and capture all that data and send it in real time over both satellite and cellular telemetry. By doing this, we're able to create dense deployed networks of distributed sensors. And those networks increase our overall spatial and temporal understanding of the ocean, which is closing that ocean data gap that exists because of existing technology. After making this, we decided we didn't want to just stop at the surface. We wanted to extend the capabilities of the spotter subsurface as well. And we started integrating off-the-shelf and known proven sensors into this technology, combining it with the surface waves with things like temperature, pressure, water quality, acoustics, and what we're here to talk about today, currents. And we're really excited with these capabilities because by combining this in this spatial distribution, we believe we can unlock the next wave of distributed spatial recognition. So with that, I'm going to hand it over to Anders, who's going to talk a little bit more about Aanderaa and their product, the DCS.
Thank you, Dan. And yes, um, we are really pleased with working together with you and having done this integration. And I will talk a little bit about the DCS that you have integrated. DCS is the Doppler current Doppler current sensor. So it's a single point Doppler sensor as opposed to our Doppler current profiling sensor. If we look at first a little bit about the background of Aanderaa, and here is just the timeline for current meters that we have made. It's multi parameter current meters. We started in 1966 with mechanical current meters, and then the first ADCP in 1994, first single point in 1996, and then you can see the timeline here, second ADCP here, and then we updated the single points, the DCS, with better capacity, and now here we arrive to the third generation of profilers, and we are now at the fourth generation of the single point Doppler current sensor that you see here. Some of the things that we have kept since the start is to make reliable and robust instruments that are capable of doing very long deployments At the start, they were capable of doing 2 years in Antarctic waters, for example, and it revolutionized the way currents were measured with the mechanical here. And then we have, of course, developed these capabilities, and we also make many other types of sensors, water quality sensors, wave sensors, and so that we integrate into our systems and to our instruments. But also our sensors are standalone in the sense that they can be integrated with serial signal to other types of platforms like the Sofar spotter platforms. Some things which we think we are proud of and that we think are good is that our sensors, they give out smart data, means that they calculate everything automatically on the fly on board. They have a motion compensation that goes for the current sensors, regardless of how they move and tilt. Every single acoustic ping is compensated for the movement, and there is an internal compass which works in all the directions and all tilts and compensate every single ping. And this we have had since the end of 1990s, and so that has been integrated on all our current measuring systems since then. And then we have a feature which is called auto beam, which removes beams which have been where there is an object, or in the case of the DCS, we do what we call upstream pinging. So the compensation for tilt and rotation, you see it here. This is how we do it with an acoustic profiler. So regardless of how it's tilting, or it can tilt up to 35 degrees and still handle the tilt, we reposition the cells when we measure currents in different levels here. So it's automatically compensated and for every single ping movement, for every single ping. And sensors, our current sensors, profiling sensors, current profiling sensors, and the single point sensors, they are all, and also our wave sensors, they are all calibrated in setups like this. We have low magnetic rooms with aluminium built robots which calibrate the sensors in multiple points. They are calibrating the tilt sensor and the compass. And that's a feature that we have on all our sensors, like if we talk about water quality sensors like oxygen, optodes, turbidity, salinity, they are multi-point calibrated in many points, and calibrations are run by automatic systems. So the profiler can handle 35 degrees of tilt. We can see that, or our Doppler current sensor, which is integrated to the Sofar platform, can handle 50 degrees of tilt. There are even scientific publications, where it has been shown that it can handle up to 60 degrees of tilt. And here you see how it works. It's only measuring the horizontal currents. It's focusing completely on the horizontal currents. It's measuring only in one cell, where you can select the cell size and the distance, starting distance of that cell. And so it's pinging horizontally, and normally, so it's using what we call forward pinging. It's pinging upstream, so it's using the 2 beams or 3 beams with positive Doppler shift, so to avoid that you measure in the wake of the instrument. So that gives exceptionally high quality on the measurements, which we will see later on here when Dan is telling us about the intercomparison that they have done. So we have this auto move that I talked about, exceptional ability to handle dynamic conditions. It's easy to integrate. We use a bus system, which makes it possible to connect as many sensors as you want, basically, to our instruments, but all our sensors also communicate with serial, and that is what Sofar is using to integrate it to their system. Smart data, everything is calculated on board automatically. For example, currents are vector averaged automatically during the measurements and tilt compensated. Power efficient. On the single point here, we use a dual pulse. So basically it's two measurements with the power of 1, which gives higher quality and a lower power. You can use it in spread mode or burst mode. It doesn't make any difference in power consumption. And if we look at the spread mode and burst mode, you see it here. Spread mode, you spread out the measurements, for example, 150 pings over a time period of 10 minutes, so they are spread out, and then the sensor automatically makes a vector averaging of these measurements, or you can use it in burst mode. Normally, spread mode gives you the true currents. Burst mode gives you the current measurements at the end of the interval. Stream pinging, I talked about forward pinging to avoid turbulence from the instrument. And then you get additional information, which I will talk about in two applications. Here you see the parameters which the sensor provide automatically. So it calculates the vector average speed, and it gives you the direction and heading and the tilt in different directions. It also gives you the strength, the signal strength, which I will talk about. That gives ability to measure particles, and it calculates the standard deviation of the speed, which I will also talk about, which gives you the ability to look at at movements of animals, for example, around the. So these sensors have been tow tank tested, many of them, and also field tested and proven in many field intercomparison, and proven to give really high quality data. So here we see an example of how you set it up using our real-time collector software. You don't need to read the details here, but you can see you can select distances, switch off transducers as you want. The real-time collector is a software. We have one software which handles all our sensors, regardless of which sensor it is, and instruments, regardless if you have 10 or 5 sensors connected to an instrument. So we have seen, I think this is a unique feature, that so many of our instruments and sensors have been tow tank tested. So more than several hundred of instruments have been tow tank tested, because this has been consistently done by some of our customers and with really good results. It's very difficult to tow tank test acoustic Doppler sensors both because of reflections against the walls, but here we have many successful examples, and here was from 2011 with the third generation of sensors. You see here the speed of the trolley versus the speed measured by the sensor, and with a really good agreement, actually better than what the specifications that we give. And here is our recent tests of the fourth generation of sensors. And here is a DCS, the same as Sofar is integrating to their system. And again, really good results on the tow tank testing. So now to two applications, which is not only about current measurements, but also that you can use this sensor for additional information. I talked about the backscatter, the signal strength, and here is one example of that is used very frequently. This is from Germany and the German waterway authorities, which have the task of keeping ship lanes open to the big harbors in Germany. The biggest in Germany is Hamburg, and that's along a river, along the Elbe River. There is a lot of sediment transports in the rivers and a lot of sediment accumulation. So what's needed here is to do measurements on sediment resuspension, sediment transport, and use this data for modeling. And with the models, you can plan the dredging activities in the German waterways. So the German water authorities, they have about 200 of our instruments. You see them here, Seaguard instruments. They are equipped with a single point current sensor and with turbidity that measures particles, salinity, oxygen, depth, and in some cases with pressure-based wave and tide sensors. And they use them to look at sediment transport. The main sensor for measuring resuspension of sediments is the optical turbidity. But the problem with the optical turbidity is that, especially in the summer period, there is limitations on how long they can be deployed without problems with fouling, because there is a lot of growth on the platforms in the biologically active period. So here you see just an example of data. This is from one of the rivers, and we can see that it's tidally driven system. If we look here at the direction measured by the Doppler current sensor, we see the water is going in and out of the river, and we can see that if we look at the speed here, it's up to 120 centimeters per second, 130 centimeters per second. So basically also varying in and out with the tides. Here we have the signal from the optical turbidity sensor, which also varies. You have resuspension, you can see at every time you have higher currents. And if we then also look at the signal strength from the sensor, we see that that also varies with the currents. So if we plot the signal strength from the acoustics on this axis here versus the logarithm of the optics of the optical sensor, we see that there is quite a reasonable relation. And this relation can then be used because the acoustic sensor, the Doppler current sensor, basically can be used with a lot of fouling on it. We have seen sensors which are 3 times bigger in size after being fouled, and they still work perfectly well. So this gives the opportunity, once you established a relation between the turbidity and the acoustic backscatter, you can continue to use this acoustic backscatter as a proxy for turbidity, even when the optical sensor starts to have some fouling issues. So that's one big advantage of that sensor. Another advantage I will show you here, and that's from a completely different application. This is from deploying landers. Here you see sensors and instruments on top of these landers. These are used to do stock assessment and studies of deep sea animals, of hadal, in the hadal zone. So hadal is basically deeper than 6,000 meters, or 4,000 to the deepest trenches, which are around 11,000 meters. These studies are done by Alan Jamieson and Jess Colbush in University of Western Australia. So here again, multi-parameter instruments deployed on the landers. The landers are deployed for short time periods, like 24 hours, and they are baited. Why? Because then they will attract animals at the seafloor, and the time it takes for the animals to arrive to the bait is used in models to assess stocks of animals at the seafloor. Also, they have cameras to take photos and film. So here we can see data from deployments. And this is again the signal strength, the backscatter of particles against particles. So on each of these stations, so we can see from the surface down to 6,100 meters. On each of these stations, 2 landers are deployed in parallel, so 2 instruments go down to the different depths here. If we look at the zoom in, we can see that when landers are approaching the bottom, we see the last 300 meters above seafloor. We see that there are increased particles, which is a normal thing. What you would expect that going closer to the bottom, because you have a boundary there. Here also at 6,100 meters, you can see here when it's zoomed in that concentrations of particles becomes higher. But what these people are interested in is to measure conditions at the sea floor. And here we see an example of that. We see here just salinity and oxygen. These are just straight lines because it's only a short deployment. It doesn't change really over time. This is from 5,100 meters. We see that the currents in blue here, they are quite low, and typically for deep sea around below 10 centimeters per second, increasing here at the end of the period. But what we can notice here is that when the lander hits the seafloor, there is a sediment cloud formed, which is measured by the increased backscatter levels of the signal strength here. But it doesn't affect any of the current measurements because the sediment cloud is just drifting with the currents, right? But what we also can see then is that you have spikes in the backscatter here during the deployment, and at the same time you have spikes in the automatically calculated standard deviation of the currents. So this is because you have animals here. So when animals arrive in the beams of the acoustic sensor, it will create increased, they don't drift with the currents, they swim in different directions, and that creates spikes in this standard deviation, and that fits perfectly with what they see on the cameras. So what they could envisage here is to have a system which is automatically detecting when you have animals around your platform, and then trigger cameras if doing longer deployments. So this was two applications, detection of animals and also then measuring particles. So I have one final slide here. How is this sensor performing when you have really high sea states and a lot of movements? Here is an example of this. This is from two separate buoys deployed off the coast of Norway. And we had deployment here for 3 years. That was when we were developing and testing wave sensors, and we were also testing how well the current sensors could handle the really dynamic environments here in the open sea off in the North Sea off coast of Norway. So two buoys deployed side or about 300 meters separated one from the other. And on each of them, there was this setup installed. Typically, this is what we installed as a standard on our buoy platforms. To measure surface currents, we put the single point Doppler current sensor above an acoustic profiler sensor, and these are placed together in a moon pool. So the single point is actually pinging through the PVC tube here and measuring the surface currents, or 1 meter below surface, pinging horizontally, and the profiler is pinging towards the bottom and measuring the entire profile. Not the entire profile, depends on how deep it is, but typically 50 meters below the buoy. And comparing then the single point from these two buoys separated by 300 meters, we see here the blue and the black in speed. Here we see that they track quite well during the deployment. And then we compare with the first cell of the profiler, which is about 3 meters below the measurements of the single point. We see that they track quite well most of the time, but sometimes we have different currents at the deeper layers here. So there are differences every now and then. So we can see that they correspond well, but if we then also check the wave measurements from these buoy platforms, there were wave sensors on these buoy platforms, we see that waves are varying here between 1 meter wave height until 7 meter wave height, and it doesn't affect the current measurements whatsoever. So we are quite sure that the quality here is good regardless of when we're reaching high wave heights. And we have examples off the coast of Norway with 18 meter maximum wave height, where the current measurement still seems to be fine. So if you're interested in any of more information about this, we have application notes on our webpage, and here are some examples which could be relevant. NOAA deployed an instrument, was supposed to come back and pick it up after 1 year. They couldn't go there, and they came back after 3 years and have 1,014 days of current and particle data. Here are deployments under the ice. Here is a lander that was knocked over by a sediment avalanche in a seismic zone, and still was measuring currents and sediment particles at the tilt of 60 degrees. Here the thing I talked about the Hadal zone. And finally, on our webpage also, of course, you will find an app note about the work we have done here together with Sofar about integrating the sensors, testing them in different situations. And my final slide here is about why we like so much to work with Sofar on the spotter platforms and why we think it's a really good match. It's because the platforms are effortless to deploy and they handle highly dynamic environments, even if they are small. And we provide a system here, a sensor, which is smart to compensate for movements and give high quality data in real time through the Sofar platform. And you don't only get currents, you get waves and air pressure and wind estimates, which you have seen already from Dan, and I think Dan will talk more about that. And so it can be used in many different applications, from research and environmental monitoring to marine transport, aquaculture, and dredging. And with this, I will hand it over to Dan.
Thanks, Anders. That's a really great summary of the work that you've done at Aldera and definitely highlights the capabilities and why we were so excited to partner with you on integrating the DCS. You mentioned how these systems work together, and that's definitely something that's incredibly important to us. It's not easy when it's not as easy as we all hope it would be to take two proven technologies, the spotter with smart mooring and the DCS, and combine them and hope that it just works. It was really critical as part of our development work to validate that this actually does what we want in the environments that we want it to perform, which is why we performed a 24-day co-located deployment with the bottom-mounted ADCP. And you can see from these readings and these reports that not only do we get excellent alignment in both the data from direction and speed, but that tilt compensation that you talked about allowed the moorings dynamics to not impact any of the readings that were received. Plus, the system that we deployed on the spotter was able to send the data in real time to our dashboard, meaning that throughout the 24 days, we could constantly check on it to see what were the wave heights and currents. How was the system doing? Was it still even there? We weren't able to get those health checks until we pulled up the ADCP using divers, which was just another pain point of this kind of comparison study that we were hoping to displace. With our system fully validated, I'd like to give an example of how these systems are being deployed by actual customers in real-world environments and leveraging just the technology that we see on both sides of these products. The example that I really like to talk about is the engineering company Boskalis. Here they are deploying a series of these systems, both near shore and far shore, around their marine construction environments. And what they're using them for is to basically make weather forecast windows for go, no-go operations. Looking at the sea state, both waves and currents, they can decide what is the best time for us to send our support craft and activate our supply missions versus is the sea state getting too rough and do we need to basically have protection of equipment, protection of life? And those types of decisions are critical for their types of operations and the size that they're doing. Having small enough systems like the spotter allow them to actually pick up the system and redeploy them as construction changes without needing large operational vessels. And the data being all delivered to the same backend means that any of their users can analyze and make these decisions in real time. What's exciting about the platform, as Anders mentioned, is that it's not limited to just the systems that you have on it, but it opens flexibility to integrate and add other systems without needing an engineer. And so you can start to imagine new modalities of what you can capture in a co-located system. An example here, you can add something like dissolved oxygen sensors at below and above the current meter, and then you can create a whole new application. For example, here you could be measuring the hypoxia rate and dissolved oxygen rates as you're getting tidal flushing, and maybe be able to do a real-time monitoring for harmful algal blooms. You can imagine that all of these things are designed to be flexible and modular. So it's really up to the end user how they want to actually engage, plug and play their actual mission op. This is just the beginning, and I'm super excited for where we continue to take this partnership and the next sets of things that we do. I can only imagine what this world would be like in helping close the ocean data gap if we put a current meter on every spotter that was deployed. having hundreds, if not thousands, of these systems out there in the world collecting data that we can be assimilated and help with modeling and climatology. I'm keen to see what kind of new data products we can work together to build. Anders mentioned backscatter, combining turbidity, using it as proxies for animal detection. How can we do that processing on those devices and help send those information real time to the key decision makers, covering large spatial areas? And the last is ecosystem. Can only imagine what we can integrate next. Always looking for y'all's ideas of what should we be focused on and what would make the most impact. Coming out later this year, we'll be adding new modalities and new sensors like acoustics, oxygen, conductivity, but the ecosystem is open and it's designed to be expanded as flexibly as possible. So really excited to see where we take this and what we do next. With that, I'm going to open up the chat and see what kind of questions that we have. We have a couple minutes to go focus on that. Um, and Anders, I'm gonna probably tap you in on a couple things, so you join me
Sure.
here.
Mhm.
Um, so first set of questions we have is around the deployment mooring and conditions and depths. So the spotter with smart mooring and a current meter, those can be moored up to 50 meters, either totally to depth, or you can add an additional amount of conventional mooring to go to a further depth of around 100 meters. Um, the most typical conditions that we see when people mount these is having the current meter be either mid-water line, so somewhere in the middle column, or having two systems so that you can actually create like a profile essentially. So one higher up in the water line, one further down. In terms of conditions, Anders mentioned some of the actual limits. For our systems that are moored, we recommend going about upwards of about 3 knots, so 1.5 meters per second in terms of currents, and waves that kind of wave and sea states above like a class 6. So like pretty tough waves and seas that these things can experience before any degradation.
I think, Dan, I didn't mention really, but on your sensors, which is optional, is you have temperature as well on the DCS, so you get temperature at that point, right?
Yeah, that's a really good call. Yeah, thank you for reminding me. So in that example, even with just adding two different current meters or adding a third temperature node in the middle, in addition to profiling temperature, you could also get a thermocline just just by having those sensors. So yeah, yeah, it's a good call out. Um, let's see what else. Uh, it's a good question for you, Anders. How durable is the DCS? Can you share how it typically performs in harsh ocean environments? I think you kind of talked about that, but maybe talk a little bit more.
Yeah, so we see that they are very durable. I mean, the longest deployments which are ongoing, they have been in like 15 years ongoing in Antarctica, for example, under the ice. And if we look at the example I presented from the German waterway authorities, they have yeah, maybe 150 instruments from which they bought with the earlier version of the DCS in 2009, and they are almost all of them are still in use, and this is really rough conditions with a lot of particles, high currents, and but basically they are more or less, yeah, sensors are sanded down, or the paint is off. You know, they are all in titanium and plastic, but the paint is off, and they don't look pretty, but they still work. So
Amazing.
durable, yes. I mean, yeah, at least 10 years, and yeah, and longer deployments. Yeah, we have, yeah, they are very durable, and
Very
have
cool.
turned out to be really reliable.
Great. Do you foresee a free floating option? Will it always need to be moored? That's a great question. Definitely get in contact with us. But yes, we have seen applications where wanting to free float a system that has a current meter or other drogue system, basically have it act as a free floating drogue to capture drifting currents is definitely an option. So these systems do not have to be moored if you do not want them to be.
Uh, on
Mhm.
a comment on that is we have several systems used in on from the ice in the Arctic mainly, drifting with ice. So on the sea ice and drifting away with winds and stuff, and then you need to, with GPS position, you can then calculate the current that they are meeting. Of course, they measure the combination of the currents that they find under the ice, but at the same time the speed of the ice drift. So you have to deduct the vector averaged GPS position kind of to get the absolute currents.
Yeah, very, very cool. Measuring things in the ice is always challenging, but super interesting. Question here of for those who buy a spotter, is there an option to keep the data private and unavailable to Sofar? Those are options. If there's something that is interest to you, definitely reach out to us and we can talk about what are the ways in which you can basically segment or chart your data. We have a big challenge with fouling and optical turbidity. Yeah, that's definitely a challenge. Any success or suggestions or recommendations for anti-fouling brushes, UV, others? Um, for us, for optical sensors, using wipers does help extend the life. There are additional challenges with that. I'm really interested and keen to try UV as a technology, but we don't have anything that uses that right now. Be love to hear Anders' thoughts on biofouling, combating, and also the benefit of using an acoustic backscatter to be a correction factor.
Yeah, I think for the optical sensors, like turbidity, and also for other sensors like conductivity and so fouling is a major problem in shallow water environments. And yeah, we have tested and developed methods for many years. There is no like silver bullet for this. UV works fine. We have many systems with the UV, but it takes power. So that's and it becomes more cumbersome, bigger and stuff. So on turbidity sensors, we are now putting copper nickel plates around the windows, and we are now trying some transparent tape, which is used on the acoustics in some cases, which is supposed to hamper or limit the fouling. But yeah, I mean, and every environment has their own issues with fouling, and it's always different from spring to summer to autumn to winter. I mean, depending on what animals and so. But yeah, it's a major. But for the DCS, basically, it doesn't have any issues with fouling. We have seen such sensors deployed on buoys, for example, in the Gulf of Mexico for like 1 year, and it's like three times bigger size of the sensor because of barnacles and things, and they still work fine. But the problem is when they took them up and redeployed them without taking off the barnacles, because then they didn't work for like half a day, because the barnacles were filled with air, and the air is a serious acoustic dampening. So yeah, that's a but
Yeah.
yeah, that's really a sensor which is low sensitivity to fouling, the Doppler current sensor.
Yeah, that makes a ton of sense, and definitely was one of the reasons we were really excited about using acoustics. That long dwell capability is really important for the spotter system. We recognize for every trip that you can save, not having to go and visit and clean your system for every day that it gets to be deployed longer is uh, money saved operationally and information and decisions made in the future.
Yeah, and
Uh,
one thing
yeah,
on the turbidity as well. We talk about fouling here, but also we see that in the case of the German navigational authorities, they are also concerned about really high particle concentrations where turbidity sensors they cannot measure because concentrations are too high. Here we see that also the Doppler current sensor can both measure the speed of the what you call fluid mud and also the concentrations. We haven't calibrated that, and we don't know how well it works, but it seems to be a relation there with the particle concentrations. And we have one of the app notes I presented measuring under the ice in the Arctic. There's a scientific paper there where there is a really good correlation between sediment trap material for a 1 year deployment and the acoustic backscatter from a DCS. So that's presented in that scientific paper.
Awesome. Got a question here around the spotter for solar panels and power and comms. Yes, the spotter is completely self-contained in terms of energy. So it's got a lithium-ion battery inside of it and solar panels, so it's completely powered by the sun, including power driven to the current meter, and anything else is subsurface. And the communications that it's using, so it's able to offload data both on cellular, using Iridium SBD, or sorry, satellite Iridium SBD, and cellular using a global modem. So depending upon what you're in range for, you can have different options for how frequently and how much data is being offloaded, including the current meter data. Yeah, go ahead.
There was one question about if in high wave activity, is there any way of keeping current meter vertical or within 35 degrees? 35 degrees does not apply to the single point. It can handle at least 50 degrees. 35 degrees, which I presented was as an example, was our current profiler. So ADCP profiler. For the single point, it can handle 50 degrees and without any significant lowering in the quality of the data. We have seen there is one publication, scientific publications describing it measuring at 60 degrees tilt. So where the scientists tested that, was it really possible? So yeah, it was. And it can handle really rough environments in terms of shaking, strumming, things like this, because every single ping is compensated for movement, for tilt, and for rotation.
Yeah, that's a good point. And I would add that from a system ConOp, the way that we help stabilize the current meter in very heavy waves, one, we have a larger surface expression, which you may have seen in some of the images, that allows it to basically keep the line as taut as possible, but also allows the spotter to have free range of movement for good wave measurements. But then we also add compliance chain and ballast chain. So it also weights the system so that it can be as upright as possible, even in pretty harsh environments. And we've tested and can measure the actual tilt that's being reported. So the tilt measurement's actually available, so you can see how this system is moving in a dynamic environment. Cool. Let's see what else we have here.
Is
Can
the
current
spot
meter be? Yeah, go ahead. Go ahead, Anders.
the DCS is powered by, is it running on internal power or spot or solar? It runs on spot or solar.
Yeah, yeah, it does.
And then there was, can the current meter be mounted on fixed pilings? Yes, it's
Yeah,
already, hundreds of this type of applications in ports and harbors, where it's mounted on a wall or on a piling, and you switch off one or two transducers, depending on if it's a river or something else.
yeah. Is there a way to adjust the depth of the current meter in the range of 6 meters water depth? So what's when we talk about a modular system, each of the links that connect the current meter to any other section, including the spotter or another payload, another node, those are all those cables are all modular. They come in different sections, everywhere from 3 meters all the way up to 65 meters in length. And each of those have connection points similar to what you would expect with underwater subsea connections. They use our actually open source protocol and connectors and bristle mouth. And so it's super easy for you to be able to take apart and reassemble. It's like plugging in a USB stick essentially. And you can reconstruct whatever ConOp you want. So if you want it to be super shallow for one deployment, you would change out the cables and move the current meter higher in the water column. And then if you wanted to then reconfigure it to add a secondary or third system in different depths, you would just basically swap them out like Legos. So absolutely can be built and redeployed for whatever mission op that you have. And they're definitely designed for at minimum a year's worth of deployment. So once deployed, they can keep it out there for a year and then recover and redeploy.
It says something about so current meter, does it reads averaged or bursts? So it it is averaging. I mean, burst. I mean, average mode is when you spread out the pings evenly over the measuring interval. Say you will measure at 10-minute interval, and you want to measure with 150 pings. Then it will be, if you put it in average mode, then it will spread out these 150 pings over the 10-minute interval, right? So it will, the sensor will wake up and ping and store the data. It doesn't cost more energy. Or if you set it in burst, it will make the 150 pings in the last minute of the interval. So it can do both, but then it's calculating the vector average currents, the standard deviation of the currents, the backscatter, the maximum tilt, and things like this. And it doesn't give out the raw data, but it has the possibility to give out the raw data, but it wouldn't make sense, I think, to try to send these 150 ping data through the spotter platform. I don't know if it makes much more sense to have ready calculated vector average currents in real time than to send raw data and try to calculate them at shore. If you use one of our instruments and log the data, we have a special setting where you can store the separate pings, and it can ping up to 25 hertz, so 25 measurements per second. But then it takes much more power. And it doesn't make sense unless you want to look at turbulence, for example.
Know that we're a little bit at time. We can maybe take one or two more quick questions, and then definitely if we missed any of them, we'll reach out and follow up, or feel free to contact us. So let me just grab a couple quick ones. Could we expect an integration with the DCPS profiling equipment? Maybe, yeah, definitely something we've talked about and super excited for what that could possibly look like. So stay
Yeah.
tuned.
Mm.
We intend to deploy in 50 meters of depth, distance, and deployment areas. Definitely reach out to us. We'd love to help consult based on bathymetry and location. What is the best deployment and location type for what you're trying to do? Um, can you get the time series data from the current meter or only the process data? You have access to both. So we send back the aggregated data, like Andres mentioned, but then you also can have access to the raw transmission or the actual reading data from the SD card of the spotter. So both are available to you. Cool. I think, yeah, there's there's a lot of great questions in
But
here.
Dan, I
Mhm.
think even if we are over time, we will try to answer all the questions by email, I think,
Yeah,
afterwards, right? So we try to follow up on every
absolutely.
question, except the one about Gulf of America, I think.
Yes. So we will definitely we'll definitely answer any of the questions that we have here that we didn't get to. If you have any other questions or would love to talk to us, you can see our contact information here. Definitely reach out. I wanted to thank Anders and everyone for joining. This was a really exciting and fun talk of products and solution that we're really proud of. And as mentioned, this session is being recorded and will be made available afterwards. Thank you so very much and have a great rest of y'all's day. Thank you, Anders.
Thank you. Bye. Are you, yeah, you're still there? And they have been